Hello, everyone. Welcome to lesson 29 of Calculus 1. Yeah, that's the lesson, Calculus 1. All right, so previously on Calculus 1, we saw how the limit of the Riemann sum ended up giving us the exact area under the curve. But unfortunately, evaluating this limit directly ends up being rather difficult. So in the next lesson, lesson 30, we're going to learn some ways of computing that more easily. But I want to go, for today's lesson, I want to go into what the limit of the Riemann sum is. So it turns out that this has a name, the limit of the Riemann sum. It's called the definite integral. What is the definite integral? It's written like this. So we have this kind of elongated S thing. It's like a very stretched out S with very small hooks. And then we have the limits of integration right here. We have the function that we're finding the area under the curve, and then we put what the variable is back here. So the definition of this is the limit as n goes to infinity of the sum from I equals 1 to n of f of xi delta x. So it's the limit of a Riemann sum. All right, so rather than writing out this limit painstakingly every time, we have this notation for it right here. All right, so let's label this notation. This, this number right here, this is called the lower limit of integration. And then the number up here is the upper limit of integration. And then the function that we are integrating is called the integrand. And remember, another way of imagining this is it's the signed area under the curve. So remember, what I mean by signed area is if it's above the x-axis, maybe like this, then that area will count as positive. But if on the other hand, we end up going below the x-axis, like down here, that will count as negative. That's what signed area means. And that's what the integral or the definite integral calculates. And the way it does it is it takes the limit of a Riemann sum. So we fill our area here with a bunch of little rectangles and we send the number of rectangles to infinity. All right. So how are we supposed to compute this? So suppose we wanted to know the signed area under the curve of some function. How do we compute the definite integral? It turns out that there's going to be three ways we're going to do that. So the first way we saw at the end of last class, we evaluate the limit of a Riemann sum. And as we saw last time, we just did that with a quadratic, but that ended up being a whole big mess. We had to be very comfortable with sigma notation, and we had to know some other facts as well. So that's usually not the best way of doing a definite integral. Another way we can do a definite integral is through geometry. So we also saw an example of that last class where we found the area under a line by using the area formulas for a triangle and a rectangle. So we could use geometry in these cases. And then the final way, and probably the way we're going to do this most often, we'll have to wait till next lesson. Next lesson, lesson 30, is very important because we'll learn probably the most effective way of computing these definite integrals. All right, so what I want to do for the rest of class today, so going over the definite integral, is I want to talk about a bunch of different properties of the definite integral. So these will be useful when we want to find areas under the curve, and we can sort of combine integrals together in certain ways and do other things with them. So I'm going to talk about all of the different properties for these. All right, so first of all, the variable that you use for your integral doesn't particularly matter. So all of these are exactly the same. So the integral from a to b of f of x dx is the same as the integral from a to b of f of t dt. And another common variable that's used is u. So the variable in the integral is often referred to as a dummy variable. And it doesn't really matter what we call this, so long as the variable here matches what's right here. All of these will end up being the same, since you're just plugging, for example, here we're plugging t into the function and then we're iterating over t's. We plug u into the function, we iterate over u's. As long as these are the same variable, all of these integrals will be the same. Now, what actually is an integral? What happens when we perform an integral? Well, all of these will end up shooting out a number. So an integral is a very fancy way of writing a number. And remember, that number is the signed area under the curve of f of x. Whenever we look at something like this, even though it has a variable in it, it's technically just a number. That number is the signed area. All right. So let's go ahead and talk about some properties of the definite integral here. There's going to be a lot of these. And these all sort of make sense when you think about them in terms of areas. So for example, well, actually, maybe this is the one exception here. If we take the integral from a to b of f of x dx and we reverse the bounds, so we put b here and a there, then it'll be the negative of what it was before. Now, why is that? Why does flipping these bounds end up giving us a negative? Well, remember that delta x is b minus a over n. So if we flip the a and the b, we end up getting negative a minus b over n. So if we have to flip these, we need a negative sign in order for them to be the same. So effectively, this negative sign right here translates into the negative sign right there. So if you ever want to reverse the order of integration, you can always do so by adding a negative sign or taking it away if there already is one. All right, so that's our first property. Next, the integral from a to a of f of x dx. Notice that this is exactly the same number here. This will always be 0, no matter what the function is. And why is that? Well, if this is our function and we have a right here, and that's the start and end of our region of area, well, this isn't an area at all. This is only a one-dimensional line, so it's not going to have any area whatsoever. So this is going to be 0. Another way we can imagine this is if we have a and a for both of these, we have a minus a, which would be 0 for delta x, giving us 0 for everything. So the integral from a number to the same number of any function whatsoever will always be 0. All right, let's say we have c being some constant value. Then the integral from a to b of c dx, the constant function, will be c times b minus a. And again, we can see why this is true by thinking of this in terms of an area. So if our function is the constant function c, and then we have a and b here, then the area under this curve will form a rectangle. And the width of this rectangle will be this length, b minus a, and then the height of this rectangle from the x-axis to our curve will be c. So this is the height times the width for our rectangle. And that's true of any constant function. All right, now let's say we had two functions added together or subtracted even. So if we have f of x plus or minus g of x, we want to find the area under the curve of these functions that are added and subtracted, then we could simply find the area under the curve for each one separately and then add or subtract them, depending on what operation we're doing. So effectively what's going on is if I want to know, say, the area of f of x put on top of g of x, I find the area of g of x and I find out how much area f will add when I put it on top of g. That's why this equation works out here. And there's similar reasoning for subtraction as well. All right, the next one is if we have that constant c again, but we have another function in there as well, then this will be the constant times the area under the curve. And the reason why this one is true is what we're doing when we multiply a function times a constant is we're stretching it. So we're stretching the graph of f of x by a factor of c. So that means that the area under this curve will be c times the area under the original curve, since we're stretching it by a factor of c. So you can move constants in and out of the definite integral here. All right, the next one can be a little bit confusing, but again, it makes sense if you think about it in terms of areas. We have the integral from a to b of f of x, and we add it to the integral from b to c of the same function, then that will be the integral as if we went all the way from a to c in a single integral. All right, now why is this one true? Well, if we plot a, b, and c here, and we have our function, the integral from a to b will be this area here. The integral from b to c will be this area right here. And if we add them together, then we have all of the area between a and c, which is this. So as long as the top bound of one equals the bottom bound of the other, you can combine them together and have the upper bound here and the lower bound there. That's one way to combine multiple integrals together. All right, we're going to have a few more of these properties, and then we'll do a few problems involving these properties. Okay, so let's suppose that f of x is greater than or equal to 0 on the interval a, b. Then the integral from a to b of f of x dx will also need to be greater than or equal to 0. And this property is more or less kind of obvious. Like if we actually look at the picture here, this function is positive throughout at least a to b. So that means that the area under the curve of something positive will have positive sign area because it's above the x-axis. And the same goes if this were negative. So if this were negative on the whole region a to b, then the definite integral would also be negative as well. All right, now kind of a corollary to this, if one function is greater than or equal to another on an interval, then the integral of the larger function over that integral will necessarily be greater than or equal to the integral of the smaller function over that integral. And again, this makes sense in terms of areas. If you have a function that's going to be higher up than another function, then there will be more area under this curve than there would be for the smaller one. All right, and then the final fact here, this one is a little bit strange, but it ends up being useful in a variety of cases. If we know that our function is sandwiched in between these two constant values, which I call little m and big M, that's true on this interval a to b, then we actually have an estimate for how big the integral of f can be. It has to be bigger than m times b minus a, but it can't be larger than capital M times b minus a. The way we can see that this is true is we can apply this theorem right here. So I know that f of x is greater than or equal to the constant function m on this interval. So that means that the integral of f will be bigger than the integral of the constant function m. But we saw earlier that the integral of a constant function is that constant times b minus a. So we have m times b minus a here. And then we could do the reverse reasoning to get this right here. So one thing you're going to find, especially if you go into Calculus 2, is that there are going to be quite a lot of integrals that are difficult or even impossible to do. So numerically approximating these integrals is kind of your next best bet. And having some kind of estimation on how large or how small it can often be very useful. All right, let's do a few problems using these properties here. All right, so for our first example, let's say that the integral from a to b of f of x dx, well, let's use specific numbers, 0 to 2 of f of x dx, let's say that's equal to 5. And then we have the integral from 0 to 4 of f of x dx, and that's 7. So the goal of this problem is to find out what the integral from 2 to 4 of f of x dx is. All right, now what this does is it uses the property that the integral from 0 to 2 of our function plus the integral from 2 to 4 must be the integral over the entire interval from 0 to 4. Now we know what the integral from 0 to 2 is. It's going to be 5. And we don't know what this is yet. That's what we're trying to figure out. And then we know the whole thing will end up being 7. So if we solve this algebraically here, we see that this integral, even though we don't know what the function is, we do know that this integral must end up being 2. So the area under this curve from 2 to 4 must be 2. We're able to do that without drawing any pictures or knowing what the function is, simply using the properties we've developed for integrals. Okay, for our next problem here, I want to do the integral from, let's do from 1 to 1 of arctangent of x raised to the arctangent of x. All right, now we could set up a Riemann sum with this, with our xi's and everything, and that would be awful, but we see right away that our a and our b are the same value. And whenever we integrate from one number to another, and that's the same number, then we know that this is going to end up being 0, no matter what crazy function we have, like arctan to the arctan. It's a very crazy function. But we know that this integral is automatically going to be 0 because the upper and lower bounds are the same. All right, let's do one final example here. And there are a bunch of other different exercises you could do with these. I encourage you to look at the homework. There are a lot of good practice problems for this. Let's say that we know that a function is always going to be in between 1 and 2 on the interval -2 to 2. So on this interval, we know that f is sandwiched in between 1 and 2. What we want to do is we want to estimate the integral from -2 to 2 of f of x dx. We want to find a lower bound for this and an upper bound for this. All right, well, we know that f of x is sandwiched in between here. So if we do the definite integral of all 3 of these, it's going to keep the same order. All right. Now we could use the fact that the integral of a constant is the constant itself times the distance between these 2 points. So this will end up being 1 times 4. That's the distance between -2 and 2. We have our function here, our integral. And then we now have 2 times the distance from -2 to 2. 2 times 4. So it turns out that whatever this function is, if it's sandwiched in between 1 and 2, then its definite integral over that same region, -2 to 2, needs to be somewhere between 4 and 8. It can't be bigger than 8. It can't be smaller than 4. Elsewise, it wouldn't have followed this condition right here. So that's what I was saying. If we know something about the function itself, then we can often estimate what the value of the definite integral is. All right, so these are all the different properties of integration, and most of them are pretty intuitive. We kind of take them for granted after a while. Now, for the next lesson, what we're going to do is we're going to learn how to compute the definite integrals without using geometry, and definitely without you looking at the limit of a Riemann sum directly. So it's going to be a very important lesson, so I will see you guys there.